Hey chemists, we're going to start the solutions unit in this lesson, and we're going to kick it off with just some vocabulary. A solution is a homogeneous mixture. That really just means it's uniform. And it's made of a solute dissolved in a solvent. Usually a solvent is the major component, but the real definition of a solvent is that it keeps its phase. You can actually make solutions where the solvent is actually the minor component and the solute is the major component. For example, sugar can dissolve in water, and you can get 200 grams of sugar and make a syrup out of only 100 grams of water, and you can still call this a solution. We still call water the solvent because it keeps its phase. But most of the time, solvent is also the major component. This is different than what's called a suspension. A suspension is frankly a heterogeneous mixture. So as opposed to salt in water or sugar in water, it's something you could actually separate by filtration. I'll write that, separable by filtration, for the most part. And then we actually have a category that we don't talk about too much in this class, but they certainly exist, and they have a lot of examples, which is called a colloid. A colloid is a dispersion of something that actually looks very homogeneous, and in fact it is, but the molecules are aggregates which exhibit what's called the Tyndall effect, which is a light scattering effect. For example, fog or whipped cream or smoke all actually count as colloidal mixtures, and they observe this special effect that's called the Tyndall, which is in a picture over here where you can actually see the scattering of light because the particles are so big. So here's just a glass of potentially salt water or sugar water, and here's another one that might contain something like a gelatin or something made out of very large particles, and you can actually see the beam from the flashlight, and that's because the particles are so big it scatters the rays of light, because the size of the particles is actually on the order of wavelengths of light. And that's usually not true for individual sugar molecules or sodium and chloride ions in salt water. Anyway, so that's just some vocabulary that distinguishes suspensions from solutions from colloids. Let's switch gears and talk about what makes things more soluble. How do we get things to be more dissolved? I broke it down into two categories. First, there's just structure effects, and I'm going to say non-polar solvents will dissolve non-polar solutes. For example, hexane is an organic non-polar liquid, or carbon tetrachloride, also a very non-polar. Think back to our bonding unit. You could picture what that molecule looks like. Totally symmetric, and it can dissolve non-polar solutes. So those go together. And likewise, polar solvents dissolve polar solutes. So this is a very wordy way of saying what most students remember as like dissolves like, which I'm not writing down on your notes because it's not a sufficient explanation of why this all happens to be true, but you can certainly remember that as a truth. Similar molecules, based on their structural effects, will interact favorably, and therefore they'll typically dissolve each other. So a polar water molecule, also a hydrogen bonding capable water molecule, can form favorable interactions with a sugar molecule. That's what this is over here. This is a sugar molecule or a sucrose molecule, and up here is a water. And because they can form similar intermolecular force attractions, they dissolve each other quite well. How else can we get things to dissolve better? The main thing is temperature. Number one, as temperature increases, one, solids are almost always more soluble. This is not true across the board, but I'm going to write it. Solids are more soluble. And gases are less soluble. Think about, again, making sugar water. If you dissolve solid sugar in water, as temperature increases, you can get more of that to dissolve. I'm going to qualify this with usually, because it's simply not always the case. But it's fair to say most of the time it is. Likewise with gases, if you heat up a carbonated beverage, your CO2 gas would become less soluble as temperature increases. Anybody who's taken a soft drink and let it warm up certainly knows that from experience. Frankly, gases depend more on pressure. So I'll make that mentioned here, depend more on pressure. Although temperature also plays a role. And that's shown in these graphs off to the right here. We have some solids in the graph on the left, things that are solid at room conditions at least. And for the most part, their solubility increases as temperature increases. There's certainly some exceptions. I see sodium sulfate and this cerium sulfate have a solubility that actually decreases with temperature. This really all has to do with a property that we haven't talked about yet called delta G, the change in Gibbs free energy for just making a solution. We will get to that later in the course, so I'll hold off on that for now, but that's what solubility is all about. And here's a graph of of gases versus temperature, and you can see as temperature increases, every single gas has a lower solubility. This is in a type of molar solubility as opposed to here, was based on mass, but they still just measure how much of something you can get into solution. So that's all qualitative stuff. Now let's get quantitative. How do we actually measure concentration? There's 4 ways that chemists use to describe the concentration of something. The one that we're going to use the most is called molarity. That is abbreviated with a capital M. And it's kind of like a chemist's density. It's a mole per liter, specifically a mole of solute per liter of the whole solution once it's all combined. The second one is unitless. It's a mole fraction, and it's abbreviated with the Greek letter chi. It looks kind of like an X. And it's kind of like mass percent, but it's not a percentage, and it's not based on mass, it's based on moles. And that's just your moles of one component over your total moles of substance. It could be one of the solute particles divided by the sum of the two, or it could be the mole fraction of the solvent divided by the total moles of everything. Moles are additive, just like mass are additive. Speaking of mass, we also have mass percent. We've used this before, but here it is again, because it's still a representation of concentration. It's the mass of some part divided by the total mass. I'll just say grams, and because it's a percentage, it's multiplied by 100. And then the one that might be the newest, because we haven't heard it yet in this course at least, is called molality. Similarly spelled, but just slightly different than molarity. There's an L in there at the end instead of an R. A molality, usually abbreviated with a lowercase italicized m, is still your moles of solute, but it's divided by your mass of solvent. And it is specifically your solute in the numerator, and it's not the whole solution, but just the solvent. Unlike molarity, which depends on volume, molality only really depends on mass, because moles also depend on mass. So molality does not change with temperature, independent of temperature. Independent of temperature. And the reason for that is because it doesn't relate to volume, so therefore it doesn't change with density, which changes with temperature. So sometimes chemists and scientists use molality because it's constant with temperature. Molarity actually can slightly change with temperature because density changes with temperature, and therefore volume can change with temperature. So let's practice this. Let's say we have a mixture that's made out of 1 gram of ethanol with 100 grams of water, and the total volume is additive. It's 101 milliliters. What are these four things? The molarity, the mole fraction, the mass percent, and the molality. Well, if I wanted the molarity would be the moles over the liters. And how do I get moles of solute from the mass? Well, I convert that grams into moles. So I have 1 gram divided by, I'll just make a note, ethanol, C2H5OH. That's 46 grams per mole. And in case I need it, you should remember water is 18 grams per mole. So to convert that 1 gram of ethanol into moles, I divide by 46. My total liters of solution would be that 101 mils, but I need to convert it into liters and divide by 1,000. So there's my moles, and there's my liters. And when you do the math, you get 0.215, and then capital M, meaning molar. That's just how you say it. Just like the large teeth that we have in the back of our mouths, molar, 0.215 molar. Let's check out mass percent right below it. Let's try that, part B. The mass percent would be the grams of the ethanol divided by the total grams. And if I look up above, I have 1.00 gram of ethanol. Masses are additive, so 100 plus 1 is 101. And then don't forget to multiply by 100. Almost forgot that in the main formula, so let me put that in there. And then this looks like it's going to be just shy of 1%, and indeed it is. If I follow my sig figs, it looks like I'd have 3. So I get 0.990%. So I'd like you to hit pause and see if you could do the other two. What's the mole fraction of the ethanol, and what's the molality of ethanol using the formulas you have up above? Okay, let's see how you did. So for the mole fraction is the moles of the part divided by the moles of everything. We already did the moles of just the ethanol. That's 1 over 46. And then how do I do the total? You just add them. So I have 1 over 46 for the ethanol. How many moles of water do I have? Well, I have 100 grams divided by 18 grams per mole, and this is a unitless number, as you can tell, and we get 0.0039. No units, that's just my mole fraction, really small. You could multiply by 100 to get 0.39 mole percent. Means essentially the same thing as long as you know which one you're talking about. Lastly, the molality. Molality is the moles of the ethanol, the part, specifically divided by the kilograms of just the water. That's really making this one different. It's just the mass of the solvent. They don't include the total. So the numerator is the same as we've done 2 other times now. It's 1 over 46. The kilograms of the solvent would be the 100 grams, but I have to divide by 1,000. And then you get something similar to the molarity, but not exactly. It's 0.217 molal, and that's how you describe that. That's molal at the end there. So that's an introduction to how we quantify and express different units of concentration, and some factors that affect solubility, and a couple of vocab verbs to just describe solutions.